Hi everybody, and welcome to the 1.7 task video, which is the 7th task of Module 1 for Math 1. We have two learning targets for today. They're the same learning targets we had for the 1.6 video, so I can create an explicit and recursive equation, whether that's for an arithmetic or a geometric sequence. And again, just like in the previous video, we're going to be focusing on explicit equations only for both types of sequences today. Now, what makes this video different than our previous lesson is that today we are going to focus on tables that don't start at 0. So, in all of our previous lessons and all of the previous examples that we did, we were always working with tables that started with 0 at the beginning for our input. Today, we're going to look at how our equation needs to change if our table doesn't start at 0. Now, in order to do this, we're going to start by doing one example where we expand our table to look for a pattern, just like we started our last video that way. After we find that pattern, we're going to jump straight to figuring out a way to write an equation without having to expand every time. So it says here, Lavina is training for a marathon. On her first day of training, she runs 4 miles and decides that she's going to run 2 more miles every day after that. Now you can see here that it's the first day of training she runs 4 miles. So that's why in the table, we start with 0 as our input and 4 as our output. We can also see that each day she's going to run 2 more miles. So the next day, our output values increased by 2, and then they increased by 2 again, and then they increased by 2 again, and our goal is to figure out how to write an equation for any day we choose. So maybe if she's training on the 100th day, how many miles is she going to run that day? Now, in order to do this, we're going to dig a little bit deeper into our patterns, just like we did last time. So I'm going to write this out in a slightly different way. I'm going to start with the 4, and then for the next row, instead of writing the number 6, I'm going to write this as 4 plus 2. For the next row, I'm going to expand this to say 4 plus 2 plus 2 more. And for the next row, I'm going to say that this is 4 plus 2 plus 2 plus 2 more. So we can see that we're using that pattern to expand and show where our numbers came from. Now, just like before, we can even write this in a little bit of a simpler way to show a deeper connection. So the first row is 4 plus 2, and we did that 0 times for the first row. We didn't add any 2's. For the next row, we have 4 plus 2, and we did that 1 time. Then we have 4 plus 2, and we added that 2 times. And again, that's because there are 0 2's here, there's 1 2 here, there's 2 2's here, and now there are 3 2's here, which is why we have 4 plus 2, and we did that 3 times. Now, in our previous video, what we had noticed was that the number of times that we added the 2 matched the input of the table. Here's where we have a little bit of a change. 1 does not match 0, unlike what we saw in our previous problem. As a matter of fact, 2 doesn't match 1, 3 doesn't match 2, and 4 doesn't match 3. But there is a connection between those numbers. The number that we see here is always the input minus 1. So the 1 could be calculated by doing 2 minus 1. This is really 3 minus 1. This is really 4 minus 1. Just because the numbers don't match doesn't mean that there's not a connection. That number is always the input minus 1, so we can use that to write our equation. Just as we saw in the previous problems, we can see that if we use, for example, M here for miles and D for days, then here we would have, or actually, yeah, D for days. So let's change this to a D. I apologize. We're going to have M of D is equal to, now our table starts with 4, and we're going to add the number 2. But this time, instead of putting parentheses D here, I'm going to put parentheses D minus 1. Because what the number is that's inside the parentheses is always 1 less than the number that we see here. So I'm going to say that by doing D minus 1. Now that's really the big change, is that if your table doesn't start with 0, we need to kind of adjust the input variable in the equation. So what do we notice that's different about the pattern in this situation as comparing it to a table that starts at 0? What I notice that's different is that the input value in the equation needs to be adjusted based on the table. So the explicit equation here would be m of d equals 4, starting with 4. I'm going to add the 2, and I'm going to do that input minus 1 times. Now let's talk in general. How could we come up with this equation if we didn't go through the process of writing this all out? Here's how we do that. When your table does not start at 0, you need to adjust your equation to get the input back to 0. So we want tables to start at 0, but if they don't, we need to get back to 0. For example, let's look at this table, which is an arithmetic sequence. What I'm noticing is that this table starts with 5, and our pattern here is that we are adding 3 each time. But just like we were talking about, our table doesn't start with 0, it starts with 4. So here's how we're going to adjust our equation. We're going to say f of x, because output, input, equals, start with 5, add the 3. So far everything is the same as what we've been doing, but then we need to get back to 0. If this is a 4, then to get to 0, we need to subtract 4. We need to back it up 4 spots. So we would say x minus 4. All you have to do is get back to 0. So you have to do x minus 4. Now, if your pattern is geometric, so in like the next sequence, we've got starting with 100, and our input starts with 7. Our pattern here is we are dividing by 2, which I'm going to rewrite as multiplying by 1/2, because I know that we can't do division in an equation. I'm going to have f of x, because the table is using the variables f and x, equals, start with 100, multiply by 1/2, and I'm going to do that. I'm going to make an exponent. I'm going to say x minus 7. And the reason I'm saying x minus 7 is that if the table starts at 7, to get back to 0, you need to subtract 7. So get back to 0. Let's take a look at a few more examples to practice this. So if I were to give you a random set of tables and not tell you that these are geometric or that these are arithmetic, the first thing you're going to want to do is look for the pattern. So if I'm looking at this table, I see that the values are 35, 30, 25, 20. It seems to me that the pattern is that we are subtracting 5 each time. Now, because of that, there are a few things that I know. I know that this is an arithmetic sequence. I know that the common difference is that I'm subtracting 5 each time. So because of that, here's how I'm going to write my equation. F of n is equal to, The table starts with 35, and I'm going to subtract 5. And now I need to adjust my equation because I'm noticing that the table starts at 3. So I'm going to write n minus 3 to get back to 0. In the next example, I'm going to look again for the pattern. So I've got 900, 300, 100, 33.3. It looks to me like the pattern is dividing by 3, which I know means that I'm going to do multiply by 1/3. Dividing by 3, which is multiply by 1/3. Dividing by 3, which is really multiplying by 1/3. What that tells me is that this is a geometric sequence with a common ratio of 1/3. So my equation is going to say g of x equals, I'm going to start with 900. My pattern is multiply by 1/3. And I'm going to do that on my exponent. I need to get back to 0, which means I'm going to write x minus 2 as my exponent. Because if I've got a 2 there, to get back to 0, I need to subtract 2. Now, what do we do if it's something crazy where we're starting with a negative number? The good news is this same exact method works. So the first thing I would do here is look for a pattern. If I've got 1, 5, 25, 125, I'm thinking my pattern is multiplying by 5 each time, which tells me that this is a geometric sequence with a common ratio of times 5. So my equation would be h of n equals, start with 1, multiply by 5, and do that, I've got to get back to 0. So if I've got a negative 27, then instead of subtracting to get back to 0, I need to add, which means I would have n plus 27 here to get back to 0. Okay, let's go ahead and look at this in a context. So you created a hilarious TikTok and it goes viral. You didn't realize it at first, but you noticed that after 5 hours, the TikTok had 800 views. The number of views is going to double every hour. We can see a couple things from the words in the table. After 5 hours, so we can see the 5 here, we have 800 views. We can see the 800 here. And the number of views doubles every hour. Doubles means multiplies by 2, which we can see here in the table as the pattern if we look at the outputs. If we want to write an explicit equation v of h to model the number of views after h hours, we're going to use the variable v for views and h for hours according to this, where the v is on the outside and the h is on the inside. So we would write v of h equals, start with 800, multiply by 2, and now remember we need to get back to 0. So if this is a 5, our exponent would be h minus 5 to get back to 0. Now we can check ourselves here. So what we could do is evaluate the function for a number that we know. For example, we know that when there were 7 hours, we should have 3,200 views. So if we find v of 7, that means take the number 7 and plug it in. So I would have 800 times 2 to the power of 7 minus 5. Now, 7 minus 5 is really 2. So on my calculator, I'm going to type in 800 to the power of 7 minus 5, 800 times 2. Almost forgot that part. That would be bad. Times 2 to the power of 7 minus 5, which is 3,200, which matches what I was expecting. If I look at the table, I can see that when the input was 7, the output was 3,200, so my equation checks out. We could also use it to predict a number that wasn't in the table. So for example, V of 3, we don't have a table that shows what happened after 3 hours, but we could predict it by plugging in the number 3 into our equation. So we would have 800 times 2 to the power of 3 minus 5. In my calculator, I would type in 800 times 2 to the power of 3 minus 5, which is 200. So even though I wasn't paying attention yet to how many views I had, after 3 hours, I probably had about 200 views. We can also try this with this problem. It says your friend wants to test your math skills. Your friend creates the table below and asks you to write an explicit equation. So term number, value, we're writing an equation called f of x. What that tells me is that the outputs are called f and the inputs are called x. So my equation would look like this. F of x is equal to, start with 10, and then let's find the pattern. Now it says 10, 13, 16, 19, so it seems to me that the pattern here is that you're adding 3 each time. So 10 plus 3. Now this time I'm not going to use an exponent because it's not multiplication. It's an addition pattern. So I'm just going to put a parentheses. And now my starting number here is -2. So to get back to 0, I would do plus 2. So x plus 2. Now we can check this equation. So we can use our equation and plug in -1. And we're hoping that when we plug in -1, we get 13. So if I plug in -1 into this equation instead of the x, I'm going to have 10 plus 3 parentheses -1 plus 2. On my calculator, I would type in 10 plus 3 parentheses -1 plus 2. And that gives me 13, which matches what I wanted to have based on the values in my table. So that checks out. I could also use this to predict a value that's not in my table. So I can see here I'm asked to find f of 3, which means the input should be 3. This table does not go up to 3. So I could predict what was going to happen by plugging in the number 3, 10 plus 3, parentheses 3 plus 2. Now that means in my calculator, I'm going to type in 10 plus 3, parentheses 3 plus 2, which is 25. So I predict that when the input is 3, my output would be 25. All right, that is it for today. Thank you guys so much for watching, and I look forward to seeing you soon.